This is Manish Verma with student number S4008906. These are all my VP task 1, 2, 3, all of them combined. Here we start on the very first page. We start with the approval from Sri Sir, and on the second page I've gotten a photo of my beam which I clicked at Red Rooster crane bin, and the major material type that was used was steel. And on the next page we calculate our moment of inertia with using the formulas. And here on the page 4 we start with the VP task 2. However, there was a slight correction that was needed from VP task 1 in calculations of moment of inertia, so I recalculated them and resubmitted them. And since my student number ends with an even number, my load starts from the right, and I got to multiply 6 by 4.24 to get 25.44 kilonewtons per meter as my uniform distributed load. My length of the beam was 2 meters, UDL that was distributed over the 1.2 meters because it's only on the 60% of the beam. And over here on page 5 we start calculating our moment reactions with the help of SkySafe platforms. We found the MA equations, and on this page we find our shear and bending moment functions, and therefore we create our shear force and bending moment diagrams with the help of free body diagrams as well. These are all the equations that we needed, and these will be used to find deflection and slope as well. And going ahead, we have our shear force diagram, and this is our BMD diagram. And to calculate deflection, we solve the M and V equations, which we are going to use now. And these are the 4 equations that I got, and we apply the boundary conditions. And these are the slope equations, so we equate the slopes, and then we find our C1 in terms of C3. Over here we calculate our deflections equations. We equate them to each other to find the value of C3, and therefore we can put the value of C3 into the C1 equation. And we continue, and we find the max deflection at X, and the max deflection at X was 1.087. There was a point where max deflection happened, and the max deflection was 0.438 millimeters at point X is equal to 1.087, and therefore we calculate our slope as well. And here we start off with the introduction, and here I introduce most of the things that I've done in the VP task 1 and 2, and I give some hints on how we are going to calculate our max stresses and max bending moments in VP task 3. Plus I've given some introduction to how my load and stuff was calculated. And we go ahead. So this is a structure that me and Sri decided on. So I calculated the moment of inertia of the structure as told by Sri Sir, and we hereby use the formula to calculate the bending stresses. So the bending stress max tensile is equal to M max times C max over I, and I got the value of M max from my previous task that I did. And here we the max that came out was 374.349 MPa. And since tensile and compression are equal, so compression becomes 374.749 as well. And continuing, we find our shear stress, the maximum shear stress. We use the formula tau is equal to V times area times Y bar divided by I over B. We first calculate our area, which comes out to be 1100. So this is all above the neutral axis, so we consider only half of the structure, and we plug in our values, and the max shear stress that comes out to be is 11.4588 MPa. And continuing, we calculate our max principal stress. So here we have our sigma x, which we calculated at the very beginning of the VP task 3, came out to be 374.349, and sigma y will be equal to 0 for everything we calculate in this task, and our tau max came out to be 11.4588. We plug in all those values, and the maximum principal stress we got was 375 MPa, and this can be confirmed by using the calculators, which I have attached a screenshot of at the end of the VP task 3. And we find the angle of the principal angles as well, which we put in the values in the formula tan 2 theta p is equal to tau xy divided by sigma x minus sigma y divided by 2. We plug in the values. The principal angle that we got was in radians, so we converted it into degrees, and the principal angle that came out was 1.75 degrees. So sigma p1 theta p1 is equal to 1.75, and our theta p2 came out to be 91.75. And we continue ahead and we calculate our max in plane shear stress. So the formula for calculating the tau max in plane is square root of sigma x minus sigma y divided by 2 to the power of 2 plus tau max square. We put in the values and we get the answer 187.82, which is approximately 188 MPa, and this can also be confirmed with the calculators that I've attached a screenshot at the very end. Similarly we calculate the angle, and we use the formula tan 2 theta s is equal to sigma x minus sigma y divided by 2 and whole divided by tau max. The answer obviously came in the radians, and we converted them into degrees, and the answers we got was 46.7 degrees and negative 43.3 degrees, which can also be confirmed at the very end screenshot of the calculators. So here we start off with our cases. So in case 1 we have our sigma x is equal to sigma y, sigma x is equal to 0 comma sigma y is equal to 0, and we use the bending moment diagrams and the shear force diagrams, where we find that the tau max is 9.158 square. Since we put in the values, we get sigma 1 is equal to plus 9.158, sigma 2 is equal to negative 9.158. And to calculate the tau max, we put in the values in the formula, which is square root under sigma x minus sigma y divided by 2 to the power of 2 plus our tau max square, which came out to be 9.158. And the angle, we use a similar formula, tau xy divided by sigma x minus sigma y divided by 2, which came out to be 2 theta p is equal to 90, so theta p1 is equal to 45 degrees and theta p2 is equal to 135 degrees. And here we have our case 2. Here we use the bending stress calculation that we did at the very beginning of the VP task 3. We use that value, which is 374.349, where tau is equal to 0 though. So sigma 1 comma 2 is equal to sigma x minus sigma y, which is 0, and we divide that by 2, so plus minus square root 3 sigma x minus sigma y divided by 2 to the square plus tau square, and we plug in the values. We get sigma 1 is equal to 374.349, which came out by adding, and by subtracting we got answer to be 0. And we use the similar formula to calculate tau max in plane, and we plug in the value of 374.349, which comes out to be 187.1745, which can also be verified by the calculators. And the angles, we use the similar formula, as we use in case 1, which comes out to be 090. So, and then we obviously divide them by 2, which comes out to be 0 and 45 degrees. And we therefore go to our case 3, where we have both sigma x and tau max. We plug in the values to get the answer. We use the similar formula, and the answer that came out was sigma 1 is equal to 13.52, which came out by adding, having the plus sign in between, and sigma 2 came out by subtracting, which we got negative 6.200. And I've defined all the how the forces act upon the structure, and we calculate the tau max in plane, and we plug in the values. We get the answer 9.8635 MPa. And here we calculate our failure planes. However, in none of the cases there was a failure that occurred, and so the allowable T was 500 and the allowable shear stress yield stress was 300, and in none of the cases these the values exceeded 500 or 300, and the ratios I've calculated them as well, and obviously I've written that there is no failure occurring. And here is the photo which I used for my calculations, and these can verify my answers and my working outs. And here we have our conclusion. All I explained in the conclusion was how I went through all my calculations and used SkySafe platform, and how I verified my calculations with the help of the calculator. And I explained I explained how I use the cases to calculate the failure planes. And that is pretty much it from my end.